This is problem 14-114 on page 761. A wet cooling tower is to cool 40 kilograms per second of water from 40 degrees to 30 degrees Celsius. Atmospheric air enters the tower at 1 atmosphere with dry and wet bulb temperatures of what's given there. Using the psychrometric chart, determine the volume flow rate of air into the cooling tower and the mass flow rate of the required makeup water. So I drew a cooling tower. It looks a little more like real cooling towers, like this. What they drew in the problem statement looks more like a milk jug in the old days. And let me put all of the data on this tower that they gave. They put air inlets on both sides. I didn't have room for that, so I just put it on one side. And I called this entrance state 1. So the air coming in comes in at state 1. This whole thing operates at 1 atmosphere. And they gave us a dry bulb, or a normal temperature, of 22 degrees Celsius and a wet bulb temperature of 16 degrees Celsius. I called the exiting air state 2. So this is an air stream. State 2 has a temperature of 32 degrees Celsius and a relative humidity of 95%. That was given in the problem statement. But there's more to it than this. This is a cooling tower, and it uses evaporative cooling to accomplish the cooling effect. And so what that means is that there is water that comes in, and I need a state for that. I called it state 3. There's water that comes in, and I gave this a symbol. Let me find it quickly. Yeah, mass flow rate of the cooling water comes in at a rate of 40 kilograms per second. It also comes in with a temperature of 40 degrees Celsius. Okay, so there's the temperature in state 3 and the flow rate. Now, they drew a pool of water in the cooling tower, and what they're doing is taking this water after it's, well, this is warm water. I'm sorry, I don't know why I said cooling water. I'm sorry. The evaporation of some of this water is what provides the cooling effect. But anyway, they extract the water to go back to the process, probably a power generation process, where the temperature, and I called this state 4, where the temperature at state 4 is 30 degrees Celsius. So this is the cool water. It's been cooled by some evaporation of itself. Now, since we need 40 kilograms per second to go back to the process and cool probably a condenser and a power generation unit, well, then we're going to have to provide some makeup water. Okay, so there will be some makeup water, and that flow rate, I gave the symbol m.H2O. Okay, both of these are flow rates of water, but this is makeup water. And the reason we need it is because some of the water that comes in evaporates off and goes out into the atmosphere. We've lost it. Now notice that I was careful where I chose state 4. I did not choose state 4 cutting both of these lines. You'll see why in just a minute in the equations. Alright, so the solution to this is to find the state information as much as possible. And so for state 1, I intersected the dry bulb, that would be a vertical line on the psychrometric chart on the horizontal axis, with the wet bulb temperature, which is the dotted line running this way. I intersected those and was able to pinpoint one particular state, the state of the humid air in state 1. That way I could read off the enthalpy. It was 45 kilojoules per kilogram of dry air. It had an absolute humidity of about 0.0089 and a specific volume of about 0.848 cubic meters per kilogram. I then went over to state 2, since I was in the psychrometric chart, and used the fact that I had the temperature and the relative humidity to find the enthalpy in state 2, which was 107 kilojoules per kilogram of dry air, and an absolute humidity of 0.0292. So those are just numbers off the psychrometric chart. While I was in the back of the book, I thought, well, I probably ought to go and look up the conditions of the water. So what I'm going to do is assume that the enthalpy in state 3 is about equal to the enthalpy of saturated liquid at 40 degrees Celsius. I'm running out of space here, so I'll probably have to break into the cooling tower with this number. But anyway, when I looked it up, I found that the enthalpy of saturated water at 40 degrees Celsius is 167.53 kilojoules per kilogram. Okay? Similarly, I looked up the enthalpy at state 4, which would be approximately the enthalpy of saturated liquid at 40 degrees Celsius, and found that that enthalpy was 125.74 kilojoules per kilogram. Okay, so these are the conditions of the water here. Now further, I assumed that the makeup water came in at 30 degrees Celsius. Okay, so I'm assuming that the temperature leaving here is 30 degrees Celsius. The makeup water is at 30 degrees Celsius. That way I can actually solve this problem. Otherwise, without that assumption, I couldn't solve the problem. Okay? So far so good? You understand the setup of the problem and how I'm getting the state data first? Okay, so then what? Well, apply the mass and energy balance. I started with the mass balance on the water, and it looks like this. The mass flow rate of the water in state 1 plus the mass flow rate, let me put a W on this. I didn't in my solution, but I want to be consistent with what I've done before. Plus the mass flow rate in state 3 of the water equals the mass flow rate in state 2 of the water plus the mass flow rate in state 4 of the water. So water comes in state 1 carried by the air and state 3, and leaves in state 2 with the air and in state 4 as saturated water, okay? Or close to it. So writing this in terms of the mass flow rate of the air, which is helpful because we're dealing with a psychrometric problem, all I would do to write down the mass flow rate of the water that's with the airstream is simply multiply the mass flow rate of the air by the humidity in the state. Okay? Now notice that the mass flow rate in state 3, I've already got a name for that. I've got m.w, so I simplified my subscript just a little bit. And then on the right-hand side, this is an airstream, so mass flow rate of air times humidity in the stream. And then state 4, well, that's not quite the same as what's going here. What's coming out here is 40 kilograms per second. Well, what's coming out here is slightly less. So what I did is I said, well, if I look at this and look at a mass balance on this section, the mass flow rate here, which is what I need, well, no, I'm sorry, the mass flow rate here, which is what I need, is equal to this mass flow rate minus this. In other words, if this is really state 4, then the mass flow rate in state 4 plus the mass flow rate of the makeup water equals the 40 kilograms per second. So since what I need here is just the mass flow rate out of state 4, I can solve for it by moving this mass flow rate to the other side. So that's what I did. Mass flow rate of the water, the 40 kilograms per second, minus the mass flow rate of the makeup water. Okay? And that would be the actual mass flow rate coming out in state 4. Okay? Does that make sense to everybody? These dots look like minus signs. They're supposed to be dots. Questions so far? Please don't hesitate to ask. All right, so then what I said was, well, wait a second. I've got the mass flow rate of the water on two sides of this equation, so it can cancel. So I can write the mass flow rate, or the negative of the mass flow rate of the makeup water, as the mass flow rate of the air, and what I did is just move this term to the other side, okay, times omega 1 minus omega 2, the absolute humidity's difference in state 1 and 2. So far so good? A couple steps in algebra there in one step. Now, if I write down the, you know what, I had a energy balance up there, didn't I? And I erased it. Did I already write the energy balance or not? I did not. Okay, well then let's write the energy balance now. The energy balance looks like this. The mass flow rate of the air times the enthalpy in state 1, that accounts for the energy coming in with the humid air, not humidified, but the humid air. Plus, where else does energy come in? Well, energy also comes in state 3. So the mass flow rate of the water in state 3 times the enthalpy of that water. Those are the two places that energy come in. That's equal to the mass flow rate of the air times the enthalpy in state 2, because this airstream carries energy out, plus the mass flow rate in state 3 I'm sorry, in state 4. And I've got an expression for that, right? I've got an expression for the mass flow rate in state 4. The mass flow rate in state 4, I've already used it in the mass balance, but it looks like this. Mass flow rate of water minus mass flow rate of makeup water. Okay, so I'm going to put that in directly. Mass flow rate of the water minus the mass flow rate of the makeup water. So that represents the flow rate coming out in state 4 times the enthalpy in state 4. Very good. Let me try again. That's just H2O. It's the makeup water mass flow rate. Okay? All right. So now that I have an expression, let's see, what do I not have? Well, I needed an expression for the mass flow rate of the makeup water, and now I've got one. Okay? So let me plug that in. So the mass flow rate of the air, enthalpy in state 1, plus mass flow rate of the water, H3, equals mass flow rate of the air, bless you, enthalpy state 2, plus, we need the mass flow rate of the water, minus the mass flow rate of the makeup water, but that's just plus mass flow rate of air, omega 1 minus omega 2. Okay? So what I did then is I solved for the mass flow rate of the air. What were we asked to find? I've forgotten. We're asked to find the volume flow rate of the air at the entrance, and also the mass flow rate of the makeup water. That's what we're asked for. So first of all, I went for the volume flow rate of the air by getting the mass flow rate of the air first. So if you solve for the mass flow rate of the air, what would you do? Well, you take this term to the other side, you take this term to the other side, and divide out by that difference, right? Because you're going to end up, let me do it in a couple of steps, you're going to end up with an m dot a h1 minus h2, right? Take this term to the other side, factor out the m dot a, equals, move this term to the other side, so write mass flow rate of water H3, but I need a negative sign on it, right, because I moved it to the other side, plus mass flow rate of water, plus mass flow rate of air, omega 1 minus omega 2 times H4. And then you can simply divide by H1 minus H2 in order to solve for the mass flow rate of the air. Okay? Notice we have all these numbers. The mass flow rate of the water is 40 kilograms per second. And we use that 2 places, so that's a known. The enthalpy from state 3, right here, that's a known. You know what? I made a mistake. In solving the equation, I didn't look at my sheet. I instead tried to solve it on the board. I've still got the mass flow rate of the air over here, and I need it on the other side. Let me try one more time. So we'll have to pull this term over as well. So we'd have mass flow rate of air H1 minus H2. That takes care of these 2 terms. But this term has to be pulled over as well. Okay? Notice there's an H4 multiplied by it. So if I pull the m dot a out, I would have minus H4 times omega 1 minus omega 2. Okay? So that takes care of basically that term. I still have a mass flow rate of water times H4. Okay, so now, what is left? Well, we've got the mass flow rate of water, H4, and we've got to move this to the other side. So minus mass flow rate of water, H3, which I could simplify and just write H4 minus H3. Now let's pull this mess to the other side in the denominator and write H1 minus H2 minus H4, omega 1 minus omega 2. And now that's gone. Because we pulled it to the other side. So there's the mass flow rate of the air. Now we have the mass flow rate of the water. As I said, that's 40 kilograms per second. We have enthalpies in all states, H3, 2, 1, and 4. So all the enthalpies are knowns. And we know the absolute humidity in state 1 and 2. So I plugged all those numbers into my calculator, and I found that the mass flow rate of the air is 28.12 kilograms per second. But they didn't want the mass flow rate of the air. They wanted the volume flow rate in state 1. So what do I do to find it? Well, multiply the mass flow rate of the air times the specific volume in state 1, and that would give it to me. Why? Because the mass flow rate of the air is kilograms per second, the specific volume is cubic meters per kilogram. the kilograms cancel, you'll have cubic meters per second, which is a volume flow rate. Okay? So since I've got 28.12, I multiplied it by 0.848, and I got about 23.84 cubic meters per second. If you're following along in the text, what do you notice? Somebody's got the book open to this problem. You see the answer there that they gave? What did they give? 23.9. Why do I have 23.84 instead of 23.9? Where's probably most of the error in this?
Rounding.
Rounding on what?
Reading off the chart.
Reading off the chart, right? That's where the most of the error would be. So I've read off several things here. Now these enthalpies should be fine. These are from a chart where I got a number, right? But these, I had to read off the psychrometric chart. So omega 1, omega 2, the enthalpies, there's probably a little bit of error in there, and I was actually happy to get that close. I'll be honest, I looked at this number first and panicked for a second. I thought, crap, that's too far off, 28 versus 23. Then I thought, wait a second, that's a mass flow. They want volume flow, so everything's okay. Then I saw that specific volume and breathed a sigh of relief. Okay, so I knew once I multiplied it, I'd get a number less than 28, and we were on the right track. So anyway, there's the volume flow rate that they asked for in state 1. The only thing to do now is to find the mass flow rate of the makeup water, but we've got an equation for that. I guess instead of an app for that, we've got an equation for that, right? So all we have to do is plug in the mass flow rate of the air, which I got along the way, 28.12 kilograms per second, multiplied by the difference. I don't know why I'm plugging this in. You know the numbers. 0.0089 minus omega 2, which is 0.0292. And you get a number that's negative, of course, but we've got a negative sign on the other side. So the mass flow rate of the makeup water, once you flip the sign, I got about 0.571 kilograms per second. What did they get again? I've forgotten. 0.5 something.
568.
568. So you can see again that the difference there is due to my error in reading off the properties from the chart. Questions, comments?